Hi everyone, I'm Tatsuya Miura from Tokyo Institute of Technology. And in this talk, I will talk about our recent result on the complete classification of planar P-elastic. And first of all, let me mention that this talk is based on the joint work with Kensuke Yoshizawa. He's now in the IMI at Fukuoka, but up to this March he was at Tohoku University. But now he has moved. Okay, and anyway, our preprint is now available on archive, and in fact, I will not enter all the necessary definitions in this talk, but rather try to explain the key ideas behind in a simple way as much as possible. So if you could be interested in our work more, please see our preprint itself for completion. Okay, so now let me start. Before looking at our main objects, P-elastic, I first review the classical notion of Euler's elastica. So Euler's elastica means a solution to a typical variational problem, which is probably the most basic example of higher-order geometric variational problem, I think. And I will define it in the next slide soon. In 1744, Euler already obtained a surprisingly detailed result for planar elastic. More precisely, he obtained a corresponding Euler-Lagrange equation and showed that any solution can be classified into several classes. And the left figure describes some example of such profiles. On the other hand, the right figure describes a real experiment by, again, a famous physicist. He's physicist Max Born. And you may see that, for example, here, this shape, an elastic rod is planarly deformed into a bent shape, and this shape resembles a part of a profile obtained by Euler, for example, this shape. Okay, so this is why the Euler's elastica model is regarded as a fundamental model of thin bending structures. And also I mentioned that Euler's elastica appears in many different contexts. In fact, there are already many known theoretical analogies, for example, with pendulum model or drop model or balloon model. And also, it is known that the elastica or its related model is applied to the field of architecture, image processing, and also many other fields. Alright, now let's give the mathematical definition of Euler's elastica. To this end, we first define the so-called bending energy. The bending energy is a quantity that measures how a given curve gamma bend. So it is, more precisely, it is defined by the line integral for planar curve gamma, and the integrand is the squared curvature. So, in this talk, we only consider planar curve. So gamma always denotes a planar curve in the Euclidean plane. And S denotes the arc length as usual, and K denotes the signed curvature function. So it is a scalar function. And the bending energy was first introduced by Daniel Bernoulli in the 18th century, and soon later, Euler published the first study about the bending energy. And it is the origin of the Euler's elastica theory. And since then, a vast amount of literature has been published, but of course I cannot exhaust them, and I don't enter the details of the history in this talk. Okay, anyway, now we define Euler's elastica. A planar curve gamma is called elastica if it is a critical point of the bending energy B under the fixed length constraint. So here this capital L denotes the length functional for planar curve gamma. And this condition is known to be equivalent that there exists a lambda, multiplier lambda, such that in the direction of any smooth and compactly supported vector varied function eta, the first derivative of the energy functional B plus lambda L vanishes. So this is due to the standard multiplier method. And now the corresponding Euler-Lagrange equation is a system for the vector varied function gamma, which is a fourth order system of ODE. But it is also known that if we rewrite this equation in terms of curvature, then the equation can be reduced to a single second order ODE here in terms of curvature. So the problem can be simplified. And thanks to this simple ODE structure, we can say that any elastica is smooth by the standard bootstrap argument. And more fortunately, we can also classify all the solutions in an explicit way. So in fact, any solution K to this ODE is known to be represented by Jacobian elliptic functions. And also by using this representation, we can even parameterize the original curve gamma in the Cartesian coordinate system in terms of Jacobian elliptic integrals and functions. So all of them were smooth, in particular, of course. So in this sense, the classical elastica problem has been completely solved. Okay, but however, I should mention that there are still many open problems in this field. For example, if we consider a boundary value problem, then we need to seek appropriate solutions that are compatible with the boundary condition. And this is in general not an easy task. And also another problem is that detecting minimal or stable solutions with respect to a given boundary condition is in general hard, except for some special cases. So there are many related open problems in this field, but in some level of critical points, the problem of Euler's elastica is already completely solved. Okay. Okay, now we turn to our main object P elastica. To this end, we need to introduce the P bending energy first, which is a natural LP counterpart of the classical bending energy. So recall that the bending energy was defined as an L2 norm of the curvature function. And the P bending energy here is defined by simply replacing the exponent 2 with the general power P between 1 and infinity. Okay, so this is quite natural definition. And apart from its naturality, there are also several motivations to study the P bending energy. For example, more than 20 years ago, this energy was introduced for applying to image processing. And as I mentioned, the classical bending energy has also been used for image processing, but the general power P here makes the model more flexible and accurate. So this P bending energy model has also been studied by many authors. And in addition, the corresponding P elastica, which is a natural critical point under the fixed length constraint, has also been studied by some people, not only as a natural extension of the elastica, but also in view of some applications to, for example, linear Weingarten surfaces. And it also has some relation with models of liquid with vertical potentials, or say trajectories of plasma particles. And I recommend the recent papers by Lopez and Pampano for the details of these applications. They contain very nice presentations about this topic. Okay, and I also mentioned several other perspectives here. The one is the ambient approach, and the ambient approach roughly means that the curve is regarded as the boundary of a set. And from this perspective, there are some studies, and also there it's the study of gradient flows, and this field is recently quite active. And to my knowledge, the first study of the gradient flow of the P bending energy is given by Okabe-Potts-Wheeler, which is a second order flow. But there are some other flows, mainly of fourth order. Okay. But anyway, there are some dynamical perspectives, and also some other studies, geometric inequalities, and so on. However, I found that the P elastica theory was not yet complete at even today. So our main aim here is to develop the P elastica theory as complete as possible. So we want to develop the P elastica theory which is as parallel as to the classical elastica theory. Okay, so now I give a rigorous definition of the planar P elastica. Okay, so let P be any exponent between 1 and infinity, and gamma be a planar curve, planar immersed curve of the Sobolev W2P class. And note that this is the most natural energy space, since our P bending energy is nothing but the LP norm of the second order derivative of the curve gamma in the arc length parameterization. So this is the most natural energy space. Okay, and then we say that the curve gamma is a P elastica if it is a critical point of the P bending energy under the fixed length constraint again. So this is a parallel definition to the classical elastica. And the only difference is the energy, BP. Okay. And in terms of the directional derivative, it is equivalent that there exists a multiplier lambda such that in any direction, the first order derivative of the energy BP plus lambda L vanishes. Okay. And the only difference is the exponent of the curvature here. Okay, by this definition, we formally derive the corresponding Euler-Lagrange equation here in form of there exists a multiplier lambda such that the curvature of the P elastica satisfies this second order ODE. Okay. This is again a second order ODE, but here I should emphasize that there is a non-trivial coefficient even in the leading order term. So, and now you see that this term may be singular if p is less than 2, because in the sense that if k is equal to 0, then this term will diverge if p is less than 2. And also this term will degenerate if p is greater than 2, in the sense that if k is equal to 0, then this term vanishes. And this difference of the structure makes the regularity problem already non-trivial. And actually we will see that the regularity of the P elastica highly depends on the exponent P. Okay. And also the classification of the solution to this ODE, or the parameterization, explicit parameterization of the original curve gamma, is quite different from the previous case. And in order to do this classification or parameterization, we need to introduce some proper new p-elliptic functions, so-called p-elliptic functions. Of course, we define this one, but in the previous case, I mentioned that we need to use standard Jacobian elliptic functions. So here we need to introduce some corresponding notions with a general exponent p. Okay, so alright, so up to here, I have emphasized what is the rigorous definition of the P elastica, and also what is the main difference from the classical case. And now I want to say something about what is known about P elastica. In fact, besides these fundamental difficulties, we have some fundamental knowledge about the P elastica. Okay, so as the striking example, I would like to mention here that Watanabe obtained many examples of planar P elasticity. Most of them resemble the profiles of the classical elasticity. I don't enter the details, but here I borrowed some figures from from the paper of Watanabe, and actually those curves quite resemble at least qualitatively, quite resemble the profiles of classical elasticity. And also, he obtained some explicit parameterizations of those planar P elasticity. And these parameterizations are partly inspired by Takeuchi's generalized elliptic integral. But here, Watanabe didn't introduce any corresponding notion of P elliptic functions, but actually he used some P elliptic integrals. Okay. And of course, these examples are already interesting, but he also obtained a quite interesting example which didn't appear in the classical case. So more precisely, he obtained some new types of profiles in the degenerate case. So namely in the case that P is greater than 2. And these curves are called flat core solutions in Watanabe's paper. So what is a flat core solutions? And the flat core solution means that it is a curve which connects some loops in some arbitrary way, in the sense that these loops, each loop have the same shape, but the direction, this plus minus directions are arbitrary. And also, any length of segment can be inserted between those loops. So in this sense, the family of flat core solutions have quite non-unique feature, and this non-uniqueness property is due to degeneracy and didn't appear in the classical case. So this would be one of the most interesting behavior in the general power P elastica. Okay. And these families are also obtained in the same paper by Watanabe. Okay. So now we have observed that Watanabe obtained some fundamental examples of planar P elastic. And also, I mentioned that some partial classification results are also obtained previously, namely by Shioji Watanabe, and this paper actually doesn't deal with planar P elastic directly, but actually they deal with P elastic in the sphere. But the techniques developed in this paper are quite useful even for planar P elastic. And also some partial classification results are obtained by Lopez and Pampano. But the complete classification of planar P elastic has not been obtained in the literature. So our goal here is to obtain the complete classification of planar P elastic. And more precisely, we want to first obtain the optimal regularity of P elastic, just starting from the natural energy space Sobolev W2P class. And also we want to classify all planar P elastic. So as we have already observed, there is a family of flat core solutions, at least in the degenerate case. And the flat core solutions have strong non-uniqueness property. So the classification is more delicate issue than the classical case. Okay. And also we want to give some explicit parameterizations to planar P elastic by introducing some new P elliptic functions and also using P elliptic integrals in order to make those explicit formulae natural extensions of the classical formulae for elastic. Okay, so these are our main goal. And this is the end of the first part of my talk. And this is about the introduction of P elastica. And in the second part of my talk, I would like to explain our main results about the complete classification of planar P elastic. Okay, thanks.